Hello everybody, and welcome back to the final video for Biostats. The last topics we'll be covering in this video are probability, chi-square, odds ratio, relative risk, number needed to treat, logistic regression, research methods, and statistical errors. So let's talk about probability. A lot of this will probably seem pretty familiar. So probability is essentially, in essence, just the proportion of times an event will occur divided by the number of possibilities times the number of tries. That may seem really complicated, but in essence, a really good model for this is something like dice, card decks, right? There's a lot of things. So when you roll a set of dice, there's 36 total possibilities, right? You can have it where the blue dice is always 1. You can have it where the black dice is always 1, and then they can have their increased numbers, blah, blah, blah. That adds up to 36, just because of 6 times 6, versus something like flipping a coin. This has 2 outcomes, right? So your probability of getting either outcome is 1/2. Versus a dice, your probability of getting, let's say you want the blue dice to be a 1 and the black dice to be a 6. There's only one outcome for that. However, there's technically 2 outcomes where you could have a 6 and a 1. And it kind of depends on what you're looking at, right? But the PE is just the number that kind of determines on average how many times an event will occur. So M is the number of ways an event can occur. This goes back to our 6 and our 1 example, right? There's 2 ways it can occur, and then the number of total possible events. There are 36 events, as we determined. So the odds of getting a 1 and a 6 specifically are 2 over 36. This is a 1 in 18. Just like with a coin flip, right? Heads or tails, 2 possibilities, odds are 1 and 2. Pretty simple. The number known as the sample space is kind of our total range of outcomes. And it just kind of determines our total possible unique events. So let's just work really quickly through this problem just to reinforce some of the math before I move on to the complement. Because this stuff is pretty basic, but I'd hate to miss a problem on this on the exam. So we'll go through it. Probability of the sum being 5. Okay, well, we know that the sum being 5, there's 4 total frequencies. This is also with dice, by the way. So we have 4 over 36. That's 1 in 9. Cool. 6 possibilities. 6 over 36 is 1 in 6. What is the probability that it'll be 10 or more? This is pretty intuitive, right? We would just do a cutoff, so we have 3, 2, 1, 6 chances. 6 over 36, same as rolling a 7 sum. It is 1 in 6. Same kind of principle, 3 or less or 11 or more. So we'd have sum being 3. This happens 1, 2 times, so that's 3 total. 11 or more, 2, 1 times. So that's 6 over 36. Again, it's 1 in 6. So again, like, it's pretty intuitive. I don't anticipate we'll get many of these, which is unfortunate because they're pretty easy. But there they are, just in case you wanted to learn probability again for the 10th year in a row. The complement's a little bit newer. It's essentially the amount of times that something is not in the probability, or not in this range that's called A, which is kind of like A is just the event that occurs, that we want to occur. So a really simple way to think about this is the probability of like A occurring, the event we want, is the probability of 1 minus not the event we're occurring, which is AC. And this is called the complement. I'm sorry, I said that backwards. A is the complement. So, and I'm trying to erase, but it's not letting me. Okay, there we go. Let's do that over. Sorry. So A is essentially the complementary event. It's everything that's not in A. Hang on. Let me double check this because I don't want to say it wrong. Okay, so the complement is denoted as AC. It's everything that is not A, which it says right here. And AC is complement. I don't know how I missed that before when I was recording. So basically, the probability of an event occurring, which is denoted as regular A without a C, is the probability of A, aka the event, is equal to 1 minus the complement. And alternatively, the probability of the complement happening, really AC, are equal to 1 minus A. They're just opposites. A is the event, AC is the complement event, or everything that is not the event. So now let's talk about three unique types of probability. We have intersect, we have conjoint, and we have conditional. Joint simply means they're like joint, or intersect, I'm sorry, is equivalent to joint. And it essentially, the way you can think of it is it's two events joined together. The probability of A occurring times the probability of B occurring. So what do we mean when we say that? Here's an example problem. The probability of drawing both is our keyword here, a queen and a heart. Well, in a deck of cards, there are 4 queens, which I believe would be right here. And then there are 13 hearts, right? And a deck of cards has 52 cards. So we just selected 4. And now we're going to select 13. So essentially, we have this math here. We have 13 and 52 for our hearts times 4 out of 52 for our queens. And when we do that, the probability of drawing both are they're about a 1% chance if we were to draw 2 cards. I think it rounds up a little closer to 2% actually, but the point remains the same. That's just the probability of getting both. So you can see that it's kind of a low probability, right? Which if we stop to think about it, it makes sense. Drawing a queen is less than a 1 in 10 chance, and drawing a heart is like a 1 in 4 chance. It's about a 1 in 40. Getting both of those is pretty unlikely. And 2% is pretty close to what we can imagine that'd be. The probability of union, or conjoint, on the other hand, is pretty much the opposite. It's the probability of A or B occurring, and not both. This is a really key emphasis for this one. It cannot be both, right? Because we have this probability here. You can see that this right here, this subtracted term, is actually equivalent to our probability of conjoint, which is not what we have in this case. We have the probability of A and the probability of B, but not the probability of both. So it's slightly different here. But to solve this, the math is still really simple. Let's just use our queen and heart example again. Right, probability of drawing a queen, 4 out of 52. Probability of drawing a heart, 1 out of 4. But then we subtract this probability. So our equation will look something like this. It'll look like 1 in 4 for those hearts, plus 1 in 13 for the queens. I'm also reducing these, by the way, in case that wasn't clear. I think this is actually 1 in 14. No, I think I'm right. I think it's 1 in 13. Okay. Sorry, I had to check myself mentally there. And then it's, sorry, not plus for that final term. It's minus the probability of joint, which we'd established was 13 over 52 times 4 over 52. When we do this math, we get, plug it in really quick. We get about 30%, right? And this looks a little more reasonable. If this term right here is 1 in 4, that's 25%. If 1 in 13 is like a little less than 10%, that would put us at around little under 35%. And then if we subtract 2, that would put us under like 33%. So you can see about 30 here is a pretty rough estimate. It also looks like in my calculator, it probably rounds up to about 31. So that makes us even closer. I just wasn't looking at too many decimal places. But yeah, so it's like, this is really nice because you can kind of logic it out, right? Just to make sure if everything seems like it should line up. And then the last type of probability we're going to talk about is conditional probability. And this one's a little more complex because while joint and union probabilities have occurred at the same time, conditional probability is essentially if one event has occurred, will a second one occur? And that doesn't necessarily mean they need to be sequential either. It can also mean if A is present, how likely is B to be present, right? So probability of event A occurring given that B has already occurred. It can be either way. It doesn't really matter what you make your A and B as long as you know what you're doing. So what is this equivalent to? Well, this is equal to our probability of conjoint over a probability of, like, let's say B in this case. B will be your first variable. And so again, it doesn't need to be in a specific order. Just whatever your initial term is what you're gonna kind of use for this. So what does this mean? You can see we also, again, have the probability of joint, but this is weird, right? Because let's look at this practice problem. We have 809 pharmacists surveyed, but this isn't like a deck of cards. There's only 3 outcomes. So how do we find our probability of conjoint, our probability of overlap? Well, what we can do is you can see if we were to add these two numbers right here, this 419 and these 572, and then I can just do that really quick just to show it off. We have 419 plus 572 over 809 total surveyed. What you find is that we actually have more than 100%, right? We have like 122% of people. How does that work? Well, the conjoint in this case is people that have both. And that's exactly what this problem is looking at. It's trying to find out how many have both. And that's what our conjoint is. So our conjoint's going to be this 292. And then B could be, depending on the problem, it could either be the number of pharmacists that have PCs, or it could be the number of pharmacists that have TV. Again, B is really arbitrary. It doesn't really matter. But let's see what it's asking about in this problem. So it says, if a pharmacist has a PC, what is the probability they also have cable TV? So, okay, in this case, it is asking us about the PC. So in this case, PB is 572. So all we have to do is we do 292, right? This is our conjoint. We just established that up here, divided by 572. Let me do that really quick. And we get a probability of about 51%. And that's all there is to it. It's essentially if one condition, aka RPC, has already been met, what are the probability that they would also have the TV, which is our conjoint. And that's how you do it. And that's pretty much everything with these probability rules. Okay, so now let's talk about chi-squared. This is probably the most math-heavy part of this exam. So if you usually like watching the math in this video, this is definitely where I tune in. Chi-square is usually nominal data. They're discrete variables, right? So they're not going to be traditionally numbers. It might be like numbers of a sample in a certain category, but that doesn't mean like a quantity, you know, like for example up here, this is our second example, we have asleep and awake. Like those aren't numbers, right? Those are either like on or off. So when using like a critical value chart, which we won't have to do for this class, but I'll talk about it anyways, degrees of freedom are n-1, pretty simple, similar things to what we've seen to t-test. You can look it up in a table, it'll give you a value based on what your alpha value is, your samples, and your degrees of freedom. So for this first problem here, I just have it pulled from the chart. It's 7.815. Let's find out how to solve this. So what is a chi-squared, essentially? In essence, a chi-squared is the sum of differences from like an expected value over the expected value just to see if there's a difference. So the key word to all of that is difference. We're just seeing if these sample values are significantly different from the expected values. So how do we do that mathematically? We have this formula. The expected values in this case are right here, right? I'll show you how to do it for a two-way chi-squared, how we could actually calculate those expected values. I could have technically done it for this one, but I didn't want to. So I'll just use what Dr. Guo provided. We can see here the difference between the observed, right? This would be this group of values. This is what we measure, the observed, and the expected, which is the same for all of these in a one-way chi-squared. It's that 11.5. It's 0.5 for this first one, 3.5 for the second, negative 1.5, negative 2. We need to square these values and then divide them by the expected value. So the square of like 0.5 would be like 0.25. Square of 3.5 is, I have no idea, but I can put it in my calculator and find out. Okay, so that squared is 12.25, and then when you divide that by 11.5, right, because we also need to divide due to this step here, you get the number 1.07, and basically you just add all those up, right? It's already been done here for us. I'll show you a little more of the written out math for this next one, which is unfortunately also longer for me. but we get this final value of 1.83. Now, when your 1.83, right, this is like your chi-squared observed value is less than your critical value, your 7.815, you fail to reject the null. It's kind of like every other test we've done so far, where if it's less, you just fail to reject. And then you're done. Your data is not statistically significant. So two-way chi-squared is a little more complicated. This would probably be the most complex math we see on this exam. So I'll go through it and hopefully explain it well. So degrees of freedom, right? Same kind of concept. It's n minus 1, so it's rows minus column. So you could do like n and m minus 1. In this case, right, it's a 2 by 3, so 2 minus 1, 1, 3 minus 1, 2, 1 times 2, 2. Perfect. Critical value, 5.99 for 0.05. Awesome. Perfect. Okay. Now for the actual math. So we can actually calculate expected values ourselves. And the way we do that is each one of like our rows, right, they go across, and our columns, they each have a defined value. This example can be a little confusing, or at least I thought this was a little confusing when I did the homework the first time before I stopped and took a look at it. You can see all these values are 20. This will not always be the case for your rows and columns, because what that allows us to have happen here is these values right here are the same, which is really nice, but it's not always going to be this nice. Like in the homework, for example, each one of your expected values is going to be different. And that really is unfortunate because you have to do 16 individual calculations just to get your final answer. But in this case, the reason they're 20, right, is because we're looking at the same groups of, I don't know, it says R. I guess we'll just assume rodents in sleep. And we're looking at them at different months in their life. So those are always going to be 20 of them, right? Like unless one passed away, but even then the study wouldn't be that good. So all the rodents stay alive. So at 3 months, maybe this drug made them sleep, 7 of them sleep, and 13 of them didn't. And then later, 9 of them slept, and then 11 did not, etc., right? So this is why we always have this 20, because all this value is on the side here. It's the sum of the values in our rows, right? So 7 plus 13 is 20, 9 plus 11 is 20, 15 plus 5 is 20. It's similar for this, however, the sums along the bottom here are the sums for our columns. So 7 plus 9 is 16, plus this 15 is 31. 13 plus 11 is 24, plus 5 is 29. So you can see these numbers aren't the same. They could potentially be the same. Our experiment wouldn't really show anything if they were, I think, but they could be. But all you need to know now that we have these values is for each expected value in this chart, we need to do the equation, the sum of the row, so 31, times the sum of the same column. So let's say we're looking at this 7 up here. Its row has 31. Its column, I'm sorry, has 31. Its row has 20. So it's 31 times 20 divided by the total number of things viewed, right? This 60, total number of samples. When we do this, we get 10.3, right? Now this 10.3 is only for this 7 up here. If we were to make like a secondary chart, or I guess this chart right here, right? This is this 10.3. However, since our column number is always constant, and in this case, our rows are always constant, like in total, it will be 10.3 down this entire column. It is different on this side though, because we have this 29. In this side, it's 29 times 20 over 60 for each of these. And let's say we're just looking at this 13, right? We're using this 20 and we're using this 29. This value would be the only 9.7. But since these are all 20s, it'd kind of be the same. If this were like a 21 and this were like a 19, these two values would be different, but it'd be the same process. So you need to find an expected value for each row and each column. When it's nicely set up like this though, and our samples are the same, we get to shortcut it a little bit, which is pretty nice. So I hope that makes sense. Feel free to rewatch that if you needed any help with the homework or anything, but that's essentially how we do it. We're finding an expected value for each individual kind of sample. So now what we need to do is it's the same equation right here. We have our expected values right here, and we have our observed values. Each one of these is its own observed value. And we're just looking for the sum, essentially. And we're seeing if that sum exceeds our 5.99 critical value. So let's do that really quick. We have 7 minus 10.3 squared plus 9 minus 10.3 squared plus 15 minus 10.3 squared, and these will all be divided by 10.3. The reason we're able to do this is because these are expecteds are all the same. In the cases where expecteds are different, you would have to do each one individually. So let's say this was like 10.5 instead. This one was like 10.7. We would only be able to do like our first term over 10.3. We need to do the second one over 10.5. And we need to do this next one over 10.7. So it's convenient, again, in this case, that we're able to just bypass this step and just do the division once. And then this we're still adding because we still have their terms on the other side. We have 13 minus 9.7 squared plus 11 minus 9.7 squared plus 5 minus 9.7 squared. And then this is all over 9.7. I'll be right back with that solved math. Give me just a second. Okay, so I just added all that up, and we get a final value of about 7. In this case, 7 is greater than our 5.99. This means we can reject the null hypothesis. And it means there's some statistical significance to our experiment. So I hope that makes sense, just finding those expected values and then doing it for each individual row and column. But with that, that's pretty much all there is to chi-squared. So if you understand that, you should be good to go for the exam. Okay, now let's really briefly talk about some specialized chi-square tests. The Yates chi-square test is basically just a chi-square test that it's harder to reach statistical significance. So you'd kind of only use this one when you know you can have it be statistically significant. I guess it's a way to show stronger significance in your paper. So you could use it instead of regular chi just to kind of like show your experiment is better or your hypothesis is better. This next test is the Fisher exact test. It's a modified chi-square test, and it's when expected values are really small or have a 0. It's a little bit weaker than a chi-square test for that reason, though. But it is good if you have really small samples or really low sample numbers. So you could use it for like a preliminary study, and it would be appropriate just to justify a bigger study. That'd be an example. The last one is the McNamer test, and it compares things before and after, kind of like a t-test, a paired t-test specifically. So it's really good for that before and after kind of nominal data. But that's pretty much everything with all the specialized chi's. I can't imagine we need to know anything more in depth than that. Moving on to odds ratios and relative risk. So these are pretty similar. These will essentially compare the probability of an event when matched up to a certain condition. And for odds ratio, it's usually used in cohort studies. Relative risk compares risk of two sample groups, and essentially what it is good for, it is good in randomized control trials. We'll talk about this a little more in the video later. Relative risk is a little bit better because randomized control trials on average are a little bit better. They're kind of like our gold standard. And the reason relative risk is a little bit better, it's a little more conservative with its output. And because you can see they're very similar formulas. It's just in relative risk, you also account for the sum of both outcomes. So you got this A and A plus B, as well as this C and C plus D, instead of the sole division. So let's do this math really quick. This is just pretty easy. Odds ratio, it's essentially looking at if a group of people have whatever condition versus a group of people don't have the first condition and don't have the second condition. So the way that we show that is this would be our A value, right? It's people with gastric ulcers that smoke. And then we have our B value, which are essentially people with no gastric ulcer that also smoke. Now, I actually like writing it a little bit different than this way, just so you don't have to do this fractional division. You can also write this as like A times D over B times C. And that's how I'm going to write it here. So what we're essentially looking at is we're looking at smokers with gastric ulcers and non-smokers without gastric ulcers in the numerator. So that's 60 times 28. And then either non-smokers with gastric ulcers or smokers without gastric ulcers, right? So this is like our secondary condition. And when we get this, when we plug this into our calculator, we get 60 times 28 divided by 45 times 23, which comes out to be 1.62. What does this mean? When interpreting like an odds ratio or a relative risk, the way you interpret your results are you do your results minus 1. So we do 1.62 minus 1. That turns into 0.62. Then we can multiply that by 100%. So we get 62%. And essentially what this shows is that smokers are 62% more likely than non-smokers to get gastric ulcers. And yeah, this also works if this number right here is less than 1. So let's say we got like 0.75, right? We could do that minus 1, and our final answer is minus 0.25. If we multiply that by 100%, we get minus 25%, which tells you what you need to know, right? People who smoke would be 25% less likely to get gastric ulcers, which doesn't really make sense knowing what we know about gastric ulcers. But for maybe another experiment, that would make a little more sense for that number to be negative. Relative risk is really similar. Unfortunately, you can't really flip this formula as easily. I guess technically you can. I've never tried it this way before, but we'll write it out this way because I'm curious now. So we can do A, right? This is our, let's just say it's smokers and gastric ulcers again because it looks like it got cut off. So we'll have our 28 times, since we can bring this up to the numerator, it'd be C plus D. So we'd have 1 plus 52. And then we'd bring this down to the denominator. So we'd have C, which we established to be 1, times A plus B. So we'd have 28 plus 45. And then when I plug this into my calculator, we get 20.32. If we subtract 1 from this, we get a score of 19.32. And this would be like 1932%. And that number seems really high, so I'm going to just check that that works out the other way, the way you traditionally do the math. I think it should, but that was the first time I'd ever done it this way, and I just wanted to test it. So we'll try it the real way. So if we do 28 divided by 28 plus 45, all this divided by 1 divided by 1 plus 52. Let me see what happens when I put that in. So I didn't write down the answers for these because these are relatively simple, and I didn't think I would struggle with the math. So we'll find out if I'm struggling with the math or not. Nope, okay, I got the same thing. Yeah, so this is essentially 19 times higher for people who smoke to get gastric ulcers in this case. So yeah, I guess that is a way to do it. Either way should work if you want to do your math, whichever way works better for you. Next up, let's just talk significance. We've seen a lot of this before. The odds ratio here is 0.6, right? Since that's less than 1, if we did 0.6 minus 1, it'd actually be a 40% lower chance. And this is statistically significant. So you take a look at our confidence interval, it doesn't cross 1, right? So that means this is statistically significant data, which is good. This means that whatever this was, it would significantly reduce it. This, on the other hand, this has an odds ratio of 3.9, right? If we do 3.9 minus 1, we get 290% after we multiply it by 100%. So this is about 3 times higher. But you can see here, this confidence interval, this crosses 1. There's a 1 in between here. So this means this is not statistically significant. We can't draw a conclusion from example 2. This one, 3.5. 3.5 minus 1 becomes 250%. That's about 2.5 times higher. And this also doesn't cross 1, right? 1's all the way over here, outside of this interval. So this is statistically significant. So we can draw a conclusion for 1 and 3, but we can't for number 2. These charts over here are kind of the same way. These are like our confidence intervals that are in the bounds of this line. And this line in the center is our 1. Anything that doesn't cross this line is statistically significant. It could be higher, like this example. It could be lower, like this example. But one like this that crosses over this boundary of 1, it doesn't matter where the mean dot is, right? Because in this one, it's about in the center. But neither of these are statistically significant. These like 3 right here, because they all cross that 1, which ruins their statistical significance. Okay, so now let's talk about number needed to treat and number needed to harm. So all it is it's the inverse of the absolute risk reduction, right? For either one, really. In this first one, we have a placebo versus a statin in terms of reducing hyperlipidemia or mortality. You can see here the placebo does less well. That kind of makes sense, right? Statins would reduce it, so it would reduce deaths. And then if you just simply subtract these 2% from each other, you get 3.3%. Now, if you write out 3.3% as a decimal, you get 0.033. If you take the inverse of that, you would get 30, or 30.3. Wow, I cannot write a 3. Okay, 30. Or 30.3, you could round to 1. This number needed to treat essentially means you need to treat 30 or 31 patients, just depending, to avoid 1 death, which, you know, isn't super great. Like, it's you'd think it'd be higher for like statins versus nothing, right? But I mean, that's still a death you're preventing for every like 30 people. So I'd say that's pretty good. Let's look at the opposite. Let's say a drug is really bad. So I believe this example is Vioxx when I pulled it. This is a pulled COX-2 inhibitor that caused like cardiovascular events. In this case, it's still an absolute value, right? So it doesn't really matter. We can do the subtraction. We do 11.5 minus 8.2, same numbers from before, so we still get that 0.033. So essentially this is 30 or 31 again. What this means is that for each 30 or 31 patients treated with Vioxx, this drug, one more patient will die or have a cardiovascular event. So that's obviously not good, but you can see really simple statistic there. So don't miss those on the test because those should be easy points. This next one, we don't really need to know the math of behind too much, but there are a few things we do need to know. So if you remember back from when we did linear regression, we were mapping continuous data and we were making like a line plot. You can also technically map like nominal data. Why you'd need to do this as a correlation, I personally don't really know. I think there's better metrics you can use. I guess sort of for this multiple example, I can show it off a little bit later. But generally, I feel like this is kind of an archaic test, personally. But what this would show is that if we have nominal data, right, if it's 1s or 0s, I believe this example was like kicking a field goal, making it or not, making it being represented as a 1. I know that'd be like 3 points generally. But yeah, just assume 1 for like you make it and 0 if you don't. So in this case, our correlation here is our number of yards, right? Like how likely are you to kick a field goal from these lines? And again, that's making it or not. So you can map this. It's not perfectly linear because realistically it's logistic, right? Like it's going to get exponentially harder very quick because I feel like, I mean, most people even without formal training could probably, after at least a few attempts, kick a football from the 20-yard line to make a field goal. But you know, like if you asked any average person to make a 50, that would suddenly drop off. And then that wouldn't get much lower from like a 50 to a 70, right? It would level out. So that's why it would look kind of like a logistic curve. To do this though, to get meaningful correlation and to linearize the model, right? to get it as like a y equals mx plus b equation, we have to actually take the log of it, of the equation. And it's written here as log e. Just think of it as ln in case we need to do it on the test, right? Just take the ln of your number, and this will essentially make the model so it looks linear. And you can put it in like an equation like this, right? Like there's a clear connection with the y-axis. It's a negative x slope. Everything works out all nicely. And what this is showing, right, is let's say x is our number of yards away from the field goal post, right, or our yard line. So if we're at the 1 yard line, we're almost guaranteed to take it, assuming, if you remember, 1 means we always make it or have made it, right? Because if we're just at the 1 yard line, this is like 3.3 minus 0.09. All of a sudden, we're like not really all that far, right? We'd be at like 3.2. That's still greater than 1, so we'd still make it. So realistically, for this model, right, anything above like, let's say, the 33 yard line roughly, just with this 0.09 being close to 0.1, we pretty much are always guaranteed to make it. But then let's say we're at like the 40 yard line, which is bigger, right? Like this negative takes over. It overcomes this 3.3. All of a sudden, or no, I'm sorry, I misspoke. So if we're doing our subtraction, right, 33 minus 23, or in this case 3.3 minus 23 times 0.1, 0.1, 3.3, right? This would bring us to 1. So you're guaranteed to make everything before the 23. But then let's say we take it to the 24, 33 or 3.3 minus 24 times 0.1. This would get us 0.9. This is like, so when it comes to our equation, right, it's either 0 or 1. You either make it or you don't. Now this means, though, as a unit of probability, you are making it like 90% of the time. Kind of. The odds ratio, this is one way to look at it, but mathematically, to linearize this, I kind of just told a lie. That's what it would look like on the logistic scale if we did it, which is great, but realistically, we want to think of linearized numbers. So the real way to interpret this, that was basically the change in the odds ratio I just showed. It's not actually the change in the yards. It would be this b value, right? E to the b, because since this model is logarithmic, we're not changing a linear amount, right? Like we're trying to make it look like this, but in reality, since we're in this weird log world, it actually looks something more like this right now. So each change here, it's actually going to be more here because this is exponential. So a change of x is 1 on a linear scale is equivalent to a change in e to the x1 on a log scale, right? Because since we're in a logarithmic world, things are changing exponentially, and since it's the natural log, it's e. And again, this math isn't too important. Don't get too confused by it. All you need to know, though, is this b value, right? This might actually be a different problem because it looks like these 9s are different. But let's say for this problem up here, right? 1 yard would be equal to e to the 1, essentially. And we would get that from times this 0.0952, right? Because it's this beta value. So it's weird, it's complicated, but just remember that everything's to the power of e, and that will make it so changes are usually a little more drastic. Something else to note, because it is also exponential, a change in 1 yard, for example, like 1 yard away, since this is 0.9, you're kind of multiplying everything by 0.9. So let's say we start at 100% times 0.9. All of a sudden it's 90%. But then we have to do 90% for another yard times 0.9. This is 81%. I know I'm not doing the greatest job explaining this, and that's because it's very conceptual. Because again, like these are still literally just probabilities. It's not actual physical change. But essentially, just remember E. Just remember E. That's all I can say. You'll be fine. Just remember E, and then B is this value. This value right here that I just erased and I'm recircling. right? This is the only thing that matters, the thing that's next to your x value. This is what you raise e to the power of. If you know that, you can do these problems, or at least you can find the change. So that was like simple linear regression, which might be very disheartening because I feel like that's the opposite of simple. Now let's do multiple. This is so complex at this point. There's so many logs and so many things going on here. We luckily don't need to really know that much about it. What we need to know though is the beta coefficient. And what is that? It's the same as this, right? It's the same as this b, but each x value has a b, like in multiple linear regression, right? Like, so this 3.36 would belong to like this beta 1. Or let's say we have this negative 0.0073 x2, sorry, this would be the beta value of, right? And it's just different for every single variable we have. This is an example about, I believe it was like getting sick from a camel biting you. In a certain area. So, right, usually bigger beta values, or at least more extreme beta values, will have more statistical significance, right? So you can see here, these significances are less than 0.05, meaning they're significant, whereas these are much higher, meaning they're not significant. But how many more times? But we can use an equation like this to find out if you were bitten by a camel, how much more likely you are of becoming sick. How do we do that? It all goes back to E and B. Remember, this is our B value. E to the B is equal to our odds ratio. And if you remember, odds ratio minus 1 from the previous slide can get us, and then all that times 100%, can show us how much more likely we are of something happening. So let's say we have a family history of getting sick, or a family history of constantly getting bit by camels. How much more likely are you to get sick? If we do E to the 3.36, we get 28.8. So if we subtract 1 from that, we get 27.8. Times that by 100%, we get 2780%. And what this number just means is you're about 28 times more likely to get sick. And that's all it is. And we can do that for every one of these individual variables, right? So we can actually even do it for these like negative variables that are in the table as well. If we look at our herd, I don't know, maybe that means if the camels are in a herd, they're less likely to bite. I really don't know what this study was looking at. But if we do e to the negative 0.0073, we get a value of 0.99, right? 1 minus, or I'm sorry, I did that backwards. If we do 0.99 minus 1, we get negative 0.01, which equates to negative 1%. The camels are in a herd, they're 1% less likely to get you sick. Which, remember, that wasn't statistically significant, but it did have an effect that was observable. So I hope that kind of makes sense. I know with the linear, I didn't do the greatest job of explaining it. But again, just really remember that the odds ratio is the e to the power of b. That's true for both of these. And the odds ratio is kind of what will show you real change in the world. Sort of, sometimes. It's weird. And it all depends on significance as well, too. But just know e to the b, and I think you'll be okay with this topic. Okay, so now let's go into some really specific types of logistic regression. You just need to know what these are. You don't need to know how to do them. Cox proportional hazard, all it is it's the same as the multiple logistic regression. It's just you also have this inclusion of a time variable, right? It's your time until event. So this is also a factor. It's essentially making it so there's two independent variable types that are doing it. This is some really advanced math. But it essentially is just looking at, based on this amount of time, how long is it until a condition happens, and then also with these comorbidities or other conditions. The Poisson regression measures the number of times something will likely occur due to multiple variables kind of influencing the outcome. So this one is more like if we let things happen more than once based on variables, how often does it occur? And you can see it kind of there's like all these different curves that'll like show it off, and then like the further out you go, the more flat they get, the more like wide they get to develop like a higher confidence interval. Um, it's again like kind of beyond the scope of this class. Um, but I'd say what I'd remember for this is that this is a log linear scale. All of these technically are, but this was like starred in the notes. So, oh, and these are good to compare like two or more levels of independent variables as well. So again, like pretty complex. This also helps with skewed data. There wasn't enough info on the slides to really go in depth about this appropriately, but just kind of know those two exist if you see them as a question. Um, this next section should be a little bit easier, luckily. It's basically just definitions, so we're pretty much through all the math and all the stats at this point, so congratulations, you're through the stats parts of stats. Um, so basically, quick definitions. Applied research is finding a problem to solve. Basic research is understanding the problem, not just solving it. Um, Types of research. We have non-experimental. So you have Jane Goodall, right? She observed chimpanzees, how they behave, gave us insight to how they do that. When she went out to the jungle in Africa, she didn't really have a task in mind she wanted them to do. She was just watching them. So that's non-experimental. Experimental is much more traditional, probably what you think of when you think of research. Um, Coming up with like a strategy, testing something, and then seeing the results explicitly. Um, Next, like time points in studies, there's two different types of ways you can do studies over a period of time, right? So these would be like, you could just do a study in a day potentially, and it wouldn't be either of these. But if you were to do a long-term study, you could do a cross-sectional study, which essentially just looks at time points, right? So it's like you could look at kids at age 2, at age 5, and then age 10 to do an experiment for each of those. And even though that would be a study over like 8 years, you'd only be doing like 3 time points. Longitudinal study, however, is kind of like constantly taking updates. You could argue that every longitudinal study is like a cross-sectional study because you can't truly be continuous unless, I guess, let's say it was a diabetes study and you had a CGM to like see if a kid randomly developed type 1 diabetes. I guess technically that'd be longitudinal if it truly was continuous. But realistically, even if it is a continuous study, right, to see when kids develop type 1 diabetes, you're probably not testing them more than once a week or even more than one a day. Granted, that's very continuous, right? You'd have 30 to hundreds of data points per year. So that's what longitudinal is. It's basically assumed to be continuous, but technically it's really not. Technically everything's cross-sectional, but just think of cross-sectional as like a few groups and longitudinal just being over a really long time. That's the best way to think about it without convoluting it. So next up, types of research. So we have exploratory research at the very bottom, right? These are like grouped from low levels of kind of thinking and difficulty to high. That doesn't mean that things at the bottom at low aren't more valuable or are more invaluable per se. They're just at a lower level of what we discover with them. So these simply will seek to investigate or discover things that are unknown, right? You can think about this as, I don't know, I guess I could, well, I don't really know what I could do. Let's say I want to discover a new like force of nature. I want to like randomly discover what happens when I mix two chemicals together. I have nothing in mind. I just want to see what happens. I get two drugs and mix them together. That would be exploratory research. Descriptive research is then kind of trying to find correlations between phenomenon, right? So it's like if I mix these two drugs and then give it to somebody or like an animal subject or something, uh, does it cause a change in the animal? Does that raise blood pressure? Does that lower blood pressure? I don't know. So it's like, and typically, right, like exploratory would be two unknown drugs. With this, it might be a drug you already know something about. Um, I guess it doesn't technically matter, but the point is you're just looking for correlations. You're looking for causes and effects with the thing you just discovered in your exploratory phase. The final, most useful phase is explanatory. This is understanding what happens. Let's say I have my two random drug substances, I give it to my animal model. At this point, I know that this will reliably lower blood pressure. And then I find out the mechanism, right? I find out that this is actually like, it kind of works like a beta blocker. It lowers heart rate by uh, depolarizing the sinoatrial node for a long period of time. Um, that would be an example of explanatory, right? Because like I know how it works, I can explain it now. But to get there, to get up to this level 3, I needed these first two levels first. And that will always generally be the case. I'm sure there's probably an example where that's not the case, but just know that you need to go from one level to the next to eventually reach explanatory, which is your highest level of understanding. Okay, so now the next definition is like what a research problem is. This is why you start an experiment, right? Uh, Generally, I guess this would be more of like why you just or you'd start descriptive or explanatory research. I guess for exploratory research, you literally could, well, even then it'd just be like what happens when you mix these two drugs, right? Going from our previous examples, this is simply what you're asking. There should always be a relationship between two variables, right? So in the case of like what would happen when we mix these two drugs, um, what would happen would be like your dependent variable and mixing your two drugs would be the independent variable. That would be a very simple and not very good study, but you could technically propose this research problem question to it. Again, what would happen, right? It's a question, and then you test it. You would, I don't know, monitor your animal model or whatever. So, yeah, that would be an example with that. In descriptive, it's a little more cut and dry, right? It'd be like, does mixing these two drugs lower blood pressure? All of a sudden, it's like, okay, our independent variable is mixing these two drugs versus like a placebo not mixing these two drugs, and then our dependent's blood pressure, right? So that fits the hypothesis a little bit better, or the research problem a little bit better. Also, all researchers need a hypothesis. It's just a statement between two or more variables, right? And it's kind of like a prediction. So for example, I could be like, I would predict mixing those two drugs together would lower blood pressure. Or my null hypothesis would be mixing those two drugs together has no statistical effect on blood pressure, right? So it's just like, we've been doing hypotheses all semesters. It's just either the thing is going to happen or the thing isn't going to happen, and not necessarily in that order either, because sometimes your null hypothesis can even be something will happen, if it's known to happen, right? Like I could say I'm going to drop my phone on the ground and it's going to fall. That would be my null hypothesis because I think gravity exists. But maybe I tie a balloon to my phone and like maybe it'll float. Maybe it's light enough. So again, you could do something like that. But yeah, we know hypotheses. I think we're good on that. So next up are biases. And bias in general is kind of like something that would introduce error into your experiment. So there's a few different types. We have systematic bias, and essentially what systematic bias is, it's kind of like the tools or methods you're using are faulty in some way. I really like this picture with the ruler, actually. You can see here, I'm not sure how well you can see it. There's like a little chip taken out of this ruler versus like this perfectly fine ruler over here. So if you were to use this ruler that's been damaged to measure things, it would eventually be off, right? Because you're measuring from the wrong line. You'd have to estimate over time that would build up. Because if you're measuring one thing, that's like, I don't know. You find an object that's like a phone. It's like 5 inches long. You measure it. Yeah, if you measure one, yeah, you might be at like 4.9, but it'd probably be fine. But if you were to measure 100 phones lined up in a row and put the ruler from end to end, you'd be a lot more likely to have error over time. So that's kind of what systematic bias is. Bias of random errors is exactly what it sounds like. It's literally you have an outlier or something. Uh, Maybe a sample is off for one reason or another. It's damaged. All of these things can introduce bias. It's usually random chance or it's like researcher error. But unfortunately, those small little errors, human error, can build up and cause something much larger. Selection bias is also researcher induced, also known as cherry picking. This would essentially be, let's say we're making a blood pressure drug again, and we have like one patient the drug works really well in out of like 10. If we were to like maybe take two people out of the study that didn't do as well, all of a sudden, our guy that did really well would pull our average way, way up and might even put it into the range of statistical significance. That would be cherry picking, and that's a bias because obviously we want our drug to work, we want to make money, and we want to help patients. But is that really the truth of what our experiment was telling us? So not always. So that's cherry picking. Funding bias would be something, this is kind of unavoidable in a lot of senses. In some cases, I'm going to have a hot take and say funding bias isn't even always bad. It's institution with more money and more resources will typically be able to put out more data. Um, is this good or bad? That's really debatable because on the one hand, it's like small scale labs without the same resources won't be as likely to get their work published, which is bad. Like, right, science is supposed to be about getting all this work heard, but on the other hand, those labs also might not have the proper tools and equipment. So that, you never really know, right? If everybody was doing everything equally, then yes, funding bias would be inherently bad, but like, I think this is probably the least bad of the types of biases, just because knowing that institutions with the best materials, the most resources, have the opportunity to publish more research, I don't think that's always inherently, at least, a bad thing. And then finally, publication bias. Uh, this one's pretty simple. This one's on like the basis of like publishers. And it's the fact that things with positive results will get published more, right? That makes sense. These like journals that like make all their money, they want positive results. They want exciting new scientific discoveries. So if something has like they accept their null hypothesis in the experiment, a publisher might not publish that, right? It's just taking up space in their journal. Now you can still submit these to like the NIH, your results, and they'll keep it in a database, but nobody might ever see that. So what can happen is results might get exaggerated, or like I mentioned before, publishers won't really necessarily put you in a journal. So again, like results aren't weighed the same, which is unfortunate. Like just because even negative results can be beneficial in some circumstances, even if it's not as marketable. So reliability is kind of like how consistent your measures are, right? I'm sure you've probably heard before like precision and accuracy. Reliability is like your precision. It's how often you're going to hit your target. And on the next slide, we'll talk about the equivalent of accuracy, which is validity. But right, it's consistency of your measure. So there's two real tried and true ways to do this. In my opinion, they're pretty much the same thing, but I'll tell you what each one is specifically. There's test retest. This is you have a group of people, right? You test whatever your experiment is on them, whatever your method is, and then what you do is you get another group of people afterwards. You do the same thing. And then if the results are the same between the two, your methods are probably pretty good. So split half reliability is you get a bunch of people and you split them down the middle and you try your method on both of them, or they do whatever. And then if they're the same, then your test is probably reliable. Which again, this is kind of the same thing, right? Because why does it matter if you start with one big group of people versus two small groups of people? I don't really know, but those are the two types. So yeah. Okay, so now let's talk about validity, which is kind of like the equivalent of accuracy, if that helps you. So this is how close the result is to the actual result. There's four main types. I hate these definitions so much. I don't love a lot of the definitions in this class. Um, but I think these are maybe the worst offenders. So I'm going to try and put these in my own words. I hope these help you a little more for the homework and for the test. I also put the originals on here just in case you copies and paste these wordings so you're familiar with both. But if you're actually interested in learning what these are, let me explain them to you in some better wording, in my opinion. So conclusion validity, it's probably the most basic. It's the one you want the most. It just means, is your conclusion correct? This definition is actually okay. This is like probably the one that's like fine. Maybe external validity is okay too, but the next two are just terrible. Internal validity will focus on essentially if the experiment measures what it is supposed to measure. So let's go back to my blood pressure drugs, right? I mentioned before they might be a beta blocker. That might be really good. Let's say I'm still doing descriptive research. I notice that these drugs will cause blood pressure, right? So I think, okay, maybe these are a vasodilator. I don't know how they're working, but I'm trying to draw a cause and effect. And since I already know in my mind that vasodilators will lower blood pressure, I make a false conclusion that they're vasodilators. This would be an example of internal validity. Um, and the fact that I did not have enough information, I did not confirm that this was actually a beta blocker. The reason they were lowering blood pressure is because they were lowering heart rate, lowering cardiac output, which led to lowering blood pressure, right? Where I assumed it was reducing resistance. And I can give you some more practical examples of internal later on because it comes a little more important in experimental design. But this is it. You kind of come to like a faulty you're not measuring the right thing, right? Because you assume you were measuring a vasodilator when instead you were measuring a beta blocker. You weren't also observing the heart rate, so it led to your conclusion being false. Which kind of when these are wrong, they'll lead back to conclusion validity, um, if that makes sense. So the next one, construct validity, is probably the least intuitive to understand. It measures if your experiment variables are correct. Um, so again, I guess we can use our example of me thinking the beta blocker is a vasodilator. This would be me looking at cardiac output, and assuming that it's the resistance that's operating. Because if you remember, cardiac output is equal to um, BPM, right, heart rate times resistance. So essentially what I might be looking at is an example of construct validity. Since my drug is a beta blocker, right? In reality, I don't know this. It would be adjusting BPM. I don't know why I drew my B as an R. Okay, there we go. Because, right, this is what a beta blocker would do. But let's say I am just looking at cardiac output, which is one way to measure it. Measure blood pressure, right? Because cardiac output can later be multiplied into blood pressure. But let's say I'm assuming I'm looking at resistance. I am looking at the wrong variable. And realistically, I'm also looking at the wrong variable here. Because what I really want at the end of the day is I want blood pressure. While I can look at cardiac output, I'm looking at the wrong um, dependent variable here, right? Because even though this is a factor of blood pressure, it's not blood pressure itself. So that would be an example of construct validity. And another one would be, I'm assuming resistance is what's influencing this variable that's already wrong. So this is me incorrectly doing the independent variable. So that's another example of construct validity. So this is just a terrible experiment I did, because I got both the independent and dependent variables wrong for what I was trying to do. When really I should have been looking at the beta blocker, I should have been looking at the heart rate, and I also should have been looking at the blood pressure. But I didn't because it was a bad experiment. And finally, external validity. This can be a pretty good tool, honestly. External validity can be used to show if a result is accurate across science, right? So let's say somebody chooses to repeat my beta blocker study where I looked at resistance and I looked at cardiac output. Hopefully, if they had a better experiment than I did, they would prove that I did not have external validity because they would be like, this drug does not increase or decrease resistance. It increases cardiac output, which leads to an increase in blood pressure because I guess overall this would technically lower blood pressure, but whatever. I keep mixing my words, but the point is, the point of external validity is that they would prove I'm wrong and nobody would be able to repeat my experiment. My experiment was not applicable to other scientists and to other experimental models. That's what external validity is. And I just erased that when I meant to circle it. Okay, there we go. Those are the validities. Honestly, I think these two are pretty intuitive. These two are not. So those are my definitions. If you want to memorize Dr. Guo's definition as well, I'd probably encourage it because he might copy paste those for the test. But that is what these are actually talking about instead of his definitions, which I really do not like. And so now let's talk about kind of study designs. Your gold standard, the best study design for a classical experimental study, right? Which when we talked about experimental studies, was kind of like traditionally what you'll do when you'll do science. It's pretty much whatever we'll do whenever we're testing a drug. It's almost always experimental. If it wasn't just like, I'm going to leave these pills out and see if people take them and see what happens, I guess that would be an observational study, but that would not be a good study. Um, we have a randomized control trial. This is your gold standard. Essentially, it will randomly break people into groups. Uh, it will have a control group, and then it will have an experimental group. Wow, look at that. It has all three words in the title. It has its randomized groups, its control group, and its experimental group. And you just observe these, you look at a change. I just break two people or like two groups randomly. I give half the people a placebo, I give half the people my beta blocker. I would monitor blood pressure. That's all a randomized control trial is. It is probably the simplest and one of the best kind of studies. These also have really high internal validity. And the reason for this is because since these groups are random, they should have a lot of variables between them. So that means if one drug really is better than the other, it's gonna show, right? It's not gonna be like covered up by some genetic marker. At least statistically, it won't be. The next ones are a little bit more complex. We have a quasi-trial, which will, similar to a randomized control trial, also break people into a control group and a treatment group. So control and treatment. What these don't do as well as the randomized control trial, however, is they'll be broken up into groups in kind of a way that's convenient, right? So let's say these groups might be people that live on the left side of town and on the east side of, or wow, left and east. That's awesome. Left side and right side of town. I guess east is more right on a globe, so I was right. But anyways, this in theory could be fine. There might not be any significant difference between living on the left side or east side of, or wow, twice, left side or right side of town. Um, but there could be. Let's say there's like a sewage line that drains into the water supply on the one side of town. All of a sudden, you might have a lot of people with more adverse effects just in this one group, right? You can't control for it. And even though that was convenient for the study, it made the study easier. It made it easier to follow. It made it easier to classify people into groups. It had less internal validity because of outside factors like that. So quasi-trials are usually weaker than randomized control trials. Although, other than that, they're pretty much the same, right? Because they break people into those groups and they do all that kind of thing. So, pragmatic trials are really unique in the fact that these trials are pretty strong, honestly. They're just different. These will kind of use like multiple groups. Sometimes they'll have a control, sometimes they won't. They might use different systems to administer treatment. These are like really good real world studies in the sense that like you're kind of adjusting care to like specific patients if it is like a medical study. And then you're seeing like different data based on those like subgroups. Um, so because of that, because these groups are so complex, pragmatic, the thing you need to remember, these have really high external validity. Right, they can be repeated in a lot of areas because there's so many factors. If they work pretty consistently in one area, they're probably going to work pretty consistently in another area. Um, so that's everything with experimental studies. When it comes to like observational studies, we have two kinds of things. We have case control and case control nested, which are technically different, sort of. Yeah, they are. They're different. I'll break these up into three. So, case control alone should be one, and nested case control should be another. So imagine there's just three subgroups here. So case controlled is pretty simple. It's kind of what you think it is. It has someone with a condition, and then a control group. Again, kind of similar to a randomized control trial. And over time, it'll just follow people and see what happens, right? It'll follow people in the one group that have, maybe it's the drug, and then it'll follow people in the other group that maybe have a placebo. And let's say these usually occur over time, right? That's why they're observational. Observational studies will usually take a lot longer and be over time. And that's we're maybe looking at the incidence of heart attack, right? So it stands to reason if our drug is still a beta blocker, people on the beta blocker would probably have less heart attacks. So that's what this case control trial might show. It might show the case, aka our beta blocker group, would have less of these kind of things. So the cohort study is a little more complex than this. So essentially what we'll do is, actually I'm going to take a water break because I'm about to cough and I've been recording for 12 minutes straight. Okay, I'm back from my break. So I wanted to reiterate case control studies because while the example I just gave isn't wrong, I don't think it is as comparable to the other two studies. And I want to really differentiate these three because we'll be given examples like this on the exam that we need to differentiate. And I want to just show off the best ways to do these. So let's start over with case control. A case control is a retrospective study. This means it has happened after these people have these conditions. So what I described probably just fell more into a nested case control, at least a little bit. It was still a case control study, but essentially when I was saying before about the case and the control, right? Let's say our case is heart attack, and our control would be none, right? No heart attack. So in this kind of retrospective study, we'd look at all these people and we'd assess their risk factors. Now, this could be the beta blocker, right? The beta blocker could be a risk factor, or it could be the opposite. It could lower the risk. It could be obesity, right? All of these patients may or may not have this, and we can assign scores to these to kind of show which factors influence it more than others. And since this is retrospective, right, we already have all this data. We don't per se need to follow them immediately. So cohort study, the next one, this is a prospective study. And what this one does is it will look at groups of people that have nothing to begin with. They have no condition. And what we will do is we will essentially, this will be a really long experiment, and we'll just wait for people to have heart attacks. And then the study might go on 5, 10, 20 years. It doesn't matter. Or it might end when all the patients have had an event of some kind. That's sort of unlikely, but it's not impossible. And then from here, we would look at these heart attacks and be like, how many of these patients that had heart attacks would be obese? How many were on beta blockers, right? Same kind of thing. It's just this one occurs at the end and we start with none. Nested case control, which is kind of more of what I described before, is a combination of the two. So with a nested, this study is a little bit of both. It's a little bit of prospective and retrospective because you start with people similar to just case control that have had a heart attack. Don't know why I put two T's. Or yes, I do. That's how you spell attack. Wow. It's one of those days. I've been recording. I just recorded drug delivery before this, so it's been quite the afternoon. And then you have none. Right, no condition. And you can look at these. If they're people that have already had heart attack, you could just straight up look at their risk factors right away, like you would a case control. But from here, for our people with none, we can let the experiment play out for a little bit, similar to a cohort study, until they get a heart attack. And then again, we can look at these risk factors. We can look at the risk factors from this group. We can look at the risk factors from this group. And overall, this will be our nested case control study, right? It's got aspects of both. So I hope that example made a little more sense and that was a little more clear. Yeah, and that only took 3 minutes. Okay, I'm glad that didn't take super long. So now let's just look at examples of these, right? This is an example of a case control, this top one, right? Because we have our exposed, our unexposed. We don't really have a time kind of value on this. Well, we kind of do, right? This is the observation period. It looks like this period is over. Right, but we have these two groups. We're looking at them. We can just confidently say this is like a case control. And then also another subcategory of trial. As you can see, this is like a randomized clinical trial, which again, we talked about before. That's just when we get groups of people, we randomize them. right? So we probably randomized some people with our heart attack example that had heart attack that didn't. That's how we do it. So for this next one, it is a cohort study. Because we're kind of looking at the occurrence of acute pancreatitis, right? That occurs while people with HIV are on these antiretroviral drugs. So we'll start at the beginning. We can see it's like one group of patients. I guess it does split here into exposed and non-exposed. But for this one, all you need to know is that since we're looking at something over like a long period of time, that means it's prospective. And that immediately eliminates case control, at least non-nested case control. And in this case, it is just cohort. This last one is a nested case control because it looks at both. Um, and you can't really tell this just by the title. I mean, you can tell that development of diabetes is occurring. So we know in some sense it's prospective, right? Because we're seeing if something is developing due to a condition. In this case, that would be antipsychotic use. But we also don't know if there's like a pre-exposed group, an exposed group, right? Like these diagrams aren't the best to show it, but this is a nested case control because there were also some people that already had diabetes. So that's kind of what we're looking at when we look at something like this. So I'd say the easiest ways to tell are those retrospective versus prospective labels. That'll immediately tell you if it'll at least eliminate one or the other. Um, And usually if it's not retrospective, it'll immediately eliminate case control. If it's prospective, that means it's always one of these two, and vice versa, right? So it's kind of easy to do that way. And then just looking at, were there people already with the condition? Because if there are people already with the condition, then you can eliminate prospective. And that's how I would rule these out, kind of. Okay, so to finish this video off, we have experimental design and errors. So when creating a study, there's really 6 things we need to look at. The first most important thing is the research problem. Why are you doing this study? Like, what are you looking at? That's all it is. Next up, hypothesis, right? What do you think is going to happen when you do the thing? Pretty simple. Next up, these are a little more advanced. You need to actually make the study. You need to find out what experiments you're going to do, what tests you're going to run at the end. You're going to conduct it. Requires getting all the funding, requires getting all the materials, requires doing it. Not super hard. Analysis, this is where stats come in. Yay, stats. And then finally, interpretation. This is when you use your stats and you use everything else to make a decision whether or not was this a good experiment, did this mean something, basically all that is. And then the most important part of kind of like a study is at the very end, the discussion or the conclusion, depending on like the study, just the format of the paper, I guess you're writing. They're kind of interchangeable most of the time. And it's just to compare your present results with published literature. So that's something I would really encourage if any of you ever go on and do research, go into pharma or anything, and you have to write a paper, is use your discussion to compare your results to other results to like kind of define why they're relevant. Because if you just say they're relevant based on like statistical tests alone, that's fine. But if you say this is relevant because this is also shown in the field, so this would be a great jumping off point to do this next or this next, it actually has some more relevance. And then you can increase collaboration, increase science, etc., etc. I put a retrospective case control study on the slide. This looks like a nested. I'm not quite sure why I put this on this slide because I just talked about that on the last slide. But I guess what I just wanted to show with this was that in something like case control, right? You can exclude people based on things. And in this case, like type 1 diabetes was the other outcome. So if there's certain outcomes in, this would be a nested case control. It doesn't say it here because this would have to be slightly prospective if these groups weren't selected at the beginning. Just in the sense that, well, okay, let me try and see what this is saying, because risk of diabetes associated with atypical antipsychotic use. Okay, so here, actually. No, this could be prospective. So what it's looking at is, I mean, this could even be a cohort study. This is a really confusing example. Maybe that's why I put this on here. Our initial condition that we're looking at, if this was a case control study, right? Because it's retrospective, we're looking at this in the past. It was people with bipolar disorder that used atypical antipsychotic. Diabetes was not our initial thought, but it was an endpoint. It was an adverse effect. And the study just concluded somewhere around here. Now, these patients developed type 1 diabetes, right? You can tell that by these circles. So type 1 diabetes, as we kind of know at this point, is genetic, right? It's total insulin deficiency of the body. We don't totally know why it works, but it's not like type 2 diabetes, which develops because of sugar imbalances in the body and obesity and all these other things. So even though this is a type of diabetes, we would exclude it because this is kind of like a random event. So I think all I wanted to show with this was that if it's a result that's very clearly unrelated to what your study's doing, even if it's like similar, remove it. I'm not sure why I put that on this slide as opposed to the last slide, but that sure was a thing I did. So we're going to move on and go into the next thing. So here are problems with experimental designs. These are generalized to all research experiments, right? Because you could have this in anything. No control group. Now in something like a cohort study, that's obviously a little different because you're not really looking at that. But if you were doing a case control study and you did not have a control group, that would be bad. So have your control groups when they're necessary. Randomization error, this kind of goes into like cherry picking or having sampling biases, right? These are bad. We've already talked about that. Not having a null hypothesis, right? That would just be like, I think this is going to happen in the experiment, and then not really saying also nothing might happen. I feel like that we all kind of did this back in like grade school science because they just had us like, what do you think's going to happen when the experiment happens? Not, they didn't make us write both, just like, I think nothing's going to happen. Um, and then just questionable conclusions, right? Either on purpose or not, right? You might just have a conclusion that's bad. You might not have thought it through. So a way to avoid this is literally just talking with your peers in the field. If they're like, hey, that seems weird, maybe look at it again. Um, yeah. Or you're either just lying to try and get published, which is also a possibility. Um, but those are like the four most common errors that are kind of universal to all experiments. So now, like specific errors to like test or experiments, is people really often confuse like standard deviation, right? If you remember, S is sample standard deviation. Wow, is this? I think this one's sigma. Sigma is population. It's not the same as standard error of the mean, right? Like because it literally includes S in it. Again, something I just Google. They measure a different thing. So standard error is kind of like how likely all the sample means are going to fall into the population mean. You can use it to create confidence intervals for that reason, where the standard deviation S is just the distance away from the mean of a sample. Another one that gets messed up a lot, I actually messed this up in my first video. I had to leave a comment on the video correcting it, so now I know not to make that mistake again. It's the difference between alpha, p, and a confidence interval. Alpha is your type 1 error, right? This is your like false positive kind of error. So your experiment is you get a positive result, but it's actually wrong. So usually we pick 0.05 for that, which is usually confused for p-value more than anything because p-value is also usually assigned to be 0.05. They're actually not related. We just like 0.05 because it's a pretty good number. It's just a small number, so that usually means we're not making a mistake if we see it, although that's exactly what type 1 error is us making a mistake. And then confidence interval is 1 minus alpha, right? So our confidence interval would be 0.95. That 95% confidence interval we're all familiar with at this point. Another thing that this is also generalized to most studies, but apparently half of all published studies don't have an adequate sample size, which is kind of crazy. That's I remember when I saw that stat, I didn't really believe it, but apparently that's true. Next up, these are common errors when it comes to like parametric tests with skewed data sets. We didn't do these, so I don't foresee us seeing this on the exam, but I thought I'd include it anyways, just in case we do. You don't do your logarithmic transformation. This would be like logistic regression, right? If you don't take it to the ln, it wouldn't be like a linear model. Let's write b plus b1 x1. There we go. So that would be wrong. And then it's also for if you did it for non-parametric data. So like again, just knowing when to use your test. So yeah. Next up, these might be on the exam. I think these would be a little more likely to see on the exam. Chi-squared, two really common problems is empty cells, right? Let's just say you have your 3x2, get some really good data. You get like, I don't know, you're measuring how many pharmacy students showed up to study lab. So you have like 20 did not, and then 50 did on this one day, and then 40 did on this one day, and then 30 did on this one day, and then 40 did not. And let's just pretend like these are the P1, P2, and P3 classes. And let's say we don't know how many people are in the P2 class. We can't have this empty cell. Something else is cells can't have a value less than 5, like just the number 5. And this is just because with these square number differences, it makes a really big impact. So what you could do instead is you could use like a Fisher's exact test, which allows you to work with numbers as small as 0. And so that can be really useful. It's a weaker test, but it is an option. And with that, I think I'm finally done. Thank goodness, this took a while. But with that, good luck on the exam. And also the quiz, if I can get this uploaded by tonight, which hopefully I can.